Hello my dear students. So, in my last class I was explaining about spectroscopic ground state for DN system. So, in the topic or in the unit unit 2 of chapter 2.1 electronic spectra of transition metal complexes. So, we were discussing about spectroscopic ground state for DN system. Okay. So, there we took an example of each system, that is a D1 system, say for example scandium, and for D2 system, so vanadium, and for D5 system manganese. So, like this we took many examples and we understood how we are going to write down the ground state for DN systems. Okay. So, here what we have to observe is according to or based on the Hund's rule, we are going to write down or understand the spectroscopic ground state for DN system. That is, so the state with the lowest J value is stable for less than half filled d orbitals, and highest J value is stable for more than half filled d orbitals, right. So, this is what we understood regarding spectroscopic ground state for DN system, right. So, next what we understood was the terms generated by ligands. So, what are the terms generated by ligands, and what are the term symbols we are going to use, and what is its degeneracy state, and how we are going to represent the terms, where we are going to use the alphabets like A, E and T, where these symbols are called as Mulliken symbols, and A is a orbitally non-degenerate term, and E is doubly degenerate term, and T is triply degenerate term. Okay. So, this is where we stopped in my previous class, and in this session we are supposed to understand about types of electronic spectra. So, if we classify the electronic spectra, mainly there are 4 general types of electronic spectra. Okay. So, while understanding all this, what you have to keep it in your mind is, so what is meant by electronic spectra, or how does it occurs. We all living in the electronic spectrum, that means we are living in between the electromagnetic radiations. So, there exists the electronic spectra. So, if we are seeing today means, that means our eye has got a capacity to observe or detect the radiations which passes in the visible region, right. So, in the same way, so the electronic spectra occurs in 4 general types. This is strictly in terms of coordination chemistry, that too especially molecular orbital theory, all those will be based on these classifications. So, where we are going to classify them into 4 different types. So, the first one is DD or ligand field spectra. Okay. So, this is the first one, and the second type of electronic spectra is ligand to metal charge transfer bands or spectra. Okay. So, bands, we can call it as bands or we can use the word spectra, and the third is the metal to ligand charge transfer bands, and the fourth is the intra ligand bands. Okay. So, these are the different general types of electronic spectra what we are going to observe. So, now let us see one by one what is meant by DD or ligand field spectra. So, as I said, so all these electronic spectra, they uses or they carry out in the presence of electromagnetic radiations. Okay. So, this spectra, that is ligand field spectra, so this occurs in the near IR or visible and UV regions. Okay. So, that is in between 10,000 to 30,000 centimeter inverse, or if we say it in nanometers, in terms of nanometers, then 1000 to 300 nanometer. Okay. So, in this wavelength we are going to see ligand field spectra. So, lower and higher frequencies are difficult to identify experimentally. So, in DD transitions, so those electrons which have lower and higher frequency are very difficult to identify, and it is limited to only in the visible region of the spectrum. So, for that purpose, so what we are going to do is we are going to use the molecular orbital theory. So, which treats these transitions are arising due to the excitation of electrons from T to G level to Eg level belonging to the metal itself. Okay. So, we all know that suppose if the electrons are present in the d orbitals, so then we are going to classify them into T to G and Eg orbitals. That means, so the possibility of the electrons to locate in the d orbital has got 5 different phases or shapes. Okay. So, which distinguishes the identical shape and point between the axis of x, y and z. Okay. So, mainly the T to G orbitals are 3. So, that is the dxy, dyz and dxz. So, these 3 belongs to T to G orbitals, and the 2 Eg orbitals are dx square minus y square and d z square. They both have different shapes and point along the axis. Okay. So, in this way, by using molecular orbital theory, which treats these transitions as arising due to the excitation of electron from T to G level to Eg level belonging to the metal itself. So, in DD electronic transition, energy gap between T to G and Eg orbitals, it depends on 3 factors, mainly in DD transition. So, the electronic transition and the energy gap between these 2 orbitals, that is T to G and Eg orbitals, it depends upon 3 main factors. So, those 3 main factors are geometry of the complex. Geometry of the complex means in what way it has been arranged. So, whether it is having a linear geometry or planar, square or tetrahedral or octahedral. So, all these matters. Okay. When we talk about the geometry of the complex, so we should consider all these observations, and also the next factor is the nature of the bonded ligand, and the third factor is oxidation state of the central metal ion. Okay. So, what is the oxidation state? So, in organic chemistry, that especially in coordination chemistry, while talking about the complexes or this topic particularly, like different types of electronic transitions, definitely so the oxidation state of central metal ion is also very important, and this is a main factor which explains about the energy gap between T to G and Eg orbitals in the DD or ligand field spectra. Okay. And the next electronic spectra is, next type is ligand to metal charge transfer bands or spectra. Okay. So, when the electronic transition takes place from a molecular orbital located primarily on the ligand, that means so here the electron transition is going to takes place in a very low energy orbital. Okay. So, that is what is called as so the electronic transition is located primarily on the ligand. That means say for example, a metal ligand bonding has been taken place. That means in p orbitals, or where the metal ligand bonding has been taken place, which will be located primarily on the ligand, and non-bonding or anti-bonding molecular orbitals that will be located primarily on the metal atom. So, then such a type of transition is called as a ligand to metal charge transfer bands. Okay. So, why we consider this type of spectra in this class means, so here the charge transfer is taking place from ligand to metal. Okay. So, that is because so here the electronic transition will takes place from the molecular orbital which has been located primarily on the ligand. So, that is why the metal charge is transferring from ligand to metal. Okay. So, that means non-bonding or anti-bonding molecular orbital will be located, which will be primarily on the metal atom. So, that is why we classify this as ligand to metal charge transfer bands. And the third type of electronic spectra is vice versa of this. That means metal to ligand charge transfer takes place here. So, that means here these metal to ligand charge transfer bands, so these involve the transition of electron from an anti-bonding or non-bonding orbital which has been concentrated on the metal atom. Okay, so from the metal atom to the anti-bonding orbital which has been located primarily on the ligand. So, the charge is going to be transferred, and that charge makes us the electron to occur the electronic transition. So, these bands are observed generally in the metal ions in the low oxidation state like so iron or tris 2,2 bipyridine iron 2 complex. So, the example is the iron complex which has been formed by bipyridine. So, it has got a lower oxidation state, that is +2 is the oxidation state in the UV region, and sometimes in the visible region also. Okay. So, for example, if you take that and observe, so there the electronic transition which is going to take place, that can be classified into this group, that is metal to ligand charge transfer bands. Okay. So, that is the third type of electronic spectra. And the fourth type is the intra-ligand bonds. Okay. So, intra-ligand bond bands means, so when an electron transition takes place from one ligand orbital to another ligand orbital, so the intra-ligand transitions are observed. Okay. So, here the electronic transition is neither between metal and ligand or ligand to metal. Here it is entirely different. That means here the electronic transition is going to take place between the two ligands. Okay. So, when electronic transition takes place from one ligand orbital to another ligand orbital, so then the transition which has been absorbed, so that is classified under the intra-ligand bands. So, they are found in UV regions and can be separated from equally intense metal ligand charge transfer bands, and they depend on the metal ligand bond strength. Okay. So, these are the four general types of electronic spectra what we are going to observe. So, next topic what we have to understand is selection rules for DD transition. What is meant by a selection rule? So, this selection rule arises from the properties of the wave functions. Okay. So, you all have studied what are the properties of wave functions in physics. If you have not studied, you will study the properties of waves in quantum mechanics. So, which I am going to start once after completing this unit, we will deal with the quantum mechanics. So, there we understand the properties of the wave functions, that is the dual nature of a wave. Okay. So, wave can act as both, it can be a particle and also it can act as a quanta or a photon. Okay. So, like that, so the dual nature of wave can be discussed in quantum mechanics. So, this selection rule what I am speaking now, so this arises from the properties of wave functions. So, here the absorption of light radiations by a sample follows certain set of rules known as selection rules. Okay. So, when light radiation falls upon any substance which is under examination, so whether that radiation is absorbed or not, so even though if the radiation is absorbed, to what extent, to how much intensity of radiation has been absorbed, so all this will depend upon is guided by certain rules, so what is called as the selection rules. Okay. So, mainly there are two selection rules. So, the first one is a spin selection rule and the second one is orbital selection rule, or it is also called as Laporte selection rule. Okay. So, now we will see one by one what is meant by spin selection rule. So, in this electronic transition may occur only between energy states with the same spin multiplicity. As the name itself says, spin selection rule means, so here the electron transition will take place only between the energy states which have same spin multiplicity. So, same spin multiplicity means the multiplicity is represented as S. Okay. So, delta S, what you are seeing is that is the change in spin multiplicity will be equal to 0. There should not be any difference in the spins of two different energy states. So, according to this rule, electronic transition from a lower to higher electronic energy level of a molecule of a sample will takes place provided the two energy levels involved in the transition are of the same spin multiplicity. So, that means so here delta S should be equals to 0, must and should. So, there should be a same spin multiplicity between the two energy states which undergoes the electronic transition, then that rule is called as spin selection rule. For example, so if we see 3T1G to 3T2G, suppose electronic transition is taking place from 3T1G to 3T2G. So, the transitions between the electronic energy levels of the crystal field is allowed by spin selection rules where 3T1G to 1T2G is not allowed. Okay. So, that means so here the transition between 3T1G to 3T2G is allowed, that is because so here the spin multiplicity is the same, whereas if we observe 3T1G to 1T2G, that is not allowed, that means so that is forbidden. So, that transition is not possible, that transition will not occur. Okay. So, here if you see this example, so the transition between 3T1G to 1T2G, so where the electronic energy levels of the crystal field are allowed by the spin selection rule. Okay. So, this is what is called as a spin selection rule. That means what we have to concentrate here is so only when the spin multiplicity is the same, then only the electronic transition may occur between the two energy states. Okay. So, that is the first rule, first selection rule. And the second one is orbital selection rule, or it is also called as Laporte selection rules. So, here for molecules having a center of symmetry, so transitions which do not involve a change in the subsidiary quantum number or azimuthal quantum number. So, azimuthal quantum number is represented by small letter L. Okay. So, that should be equal to 0. That means the electronic transition will take place only when the subsidiary quantum number or azimuthal quantum number is equals to 0 or forbidden. Okay. So, suppose if we observe the quantum number of the electrons which are having center of symmetry, which possesses the transition and which do not involve the change in the quantum number. So, those type of transitions are not allowed and they are called as forbidden transitions. So, these forbidden transitions are also called as Laporte forbidden transitions, because so here we are observing that delta L is equals to 0. Okay. So, the transition which involve a change in subsidiary quantum number or azimuthal quantum number, suppose delta L is equals to 1. So, then such transitions are called as Laporte allowed transitions. Okay. So, here what we have to observe is so when there is no change in the quantum number. Okay. So, during that too especially for molecules which are having center of symmetry. So, those transitions which do not involve the change in the subsidiary quantum number or azimuthal quantum number, so they are forbidden. Forbidden means so such a type of electronic transitions could not take place. That means definitely there should be, means the transitions which involve a change in the subsidiary quantum number or azimuthal quantum number. So, only such a type of transitions are allowed and those are called as Laporte allowed transitions. Okay. So, this is the second type of selection rule what we have to concentrate on. Okay. And the next topic what we have to understand is here. So, I already have used many times like forbidden transition, forbidden transition. What is meant by a forbidden transition? Let us understand what is meant by a forbidden transition. So, this is an example. So, what is meant by forbidden transition means so if the ground and excited states for a possible transition possess the required characteristics means, so these are the characteristics. So, these two, spin selection rule and orbital selection rule, what we understood just now. So, those are the required characteristics. Suppose if the ground state and excited states for a possible transition possess the required characteristics, then the transition is said to be allowed, otherwise it is called as forbidden. Okay, understood? Here, if it obeys the spin selection rule. Okay, so here the spin selection rule says that, so when the electronic transition takes place from lower to higher electronic energy level, so definitely there should be means the spin of the two energy levels should be equal. So, the spin multiplicity should be equal or else the delta S, the change in spin multiplicity will be equal to 0. So, this is one selection rule, and another one is suppose if the electronic transition takes place from subsidiary azimuthal number or quantum number is not changed, then the transition is not allowed. Okay, so, only when there is a change in the quantum number from subsidiary quantum number or azimuthal quantum number, so then only the electronic transitions is allowed. So, these are the required characteristics. Suppose when an electronic transition takes place from ground state to excited state, if the energy states or the electron which is going to excite from lower energy state to higher energy state meets the required characteristics, then only transition is allowed, otherwise it is called as forbidden transition. Okay. So, allowed transitions involve promotion of electrons without change of spin. Okay. So, spin forbidden transitions involve change of spin and are less intense. Okay. So, this is what is known as forbidden transition. So, here if you see this representation, this diagram, so it clearly says that here, so from T 1T 2G to the 3 to T 2G, so here the spin forbidden transition is observed. Okay. So, here the energy gap also could be measured, the change in energy will be in terms of h nu. So, in some cases electronic transition which are spin forbidden give a weak absorption band, that is weak absorption means the band intensity will be low. One of the reasons for spin forbidden transition becomes partly allowed in spin orbit coupling. Okay. For example, if you take electronic transition from 1s to the 3p which is a spin forbidden. Okay. So, the electronic transition from 1s to 3p is a spin forbidden, because here the spin multiplicity is different. Okay. So, from one has got one spin multiplicity and other is a 3, that means 1s to 3p is a spin forbidden, but the spin orbit coupling will split the excited 3p state into 3p naught, 3p1 and 3p2 states. Okay. So, so here if you see this excited state, this 3p will have 3 different states, 3p will get 3 different states, that is one is 3p naught and another is 3p1 and 3p2 states. Since the resultant angular momentum which we call as J of 3p naught and ground state 1s naught is same. So, here if you see, so this is the ground state, so here 1s naught, 3p naught both are same, resultant angular momentum is the same, these two states will combine or mix to produce a new state. Okay. So, by combining, so these two are going to combine and they are going to form a new orbiter. orbit. So, that new state, one of which will be little above the 3 p naught and a little above 1 s naught. So, this is a little above the 1 s naught, and this will be this energy state will be a little below, which has been formed by 1 s naught, and which has been formed a new energy state which has been formed by 3 p naught will be little above. Okay. So, the lower new state from 3 p naught and higher new state from 1 s naught will have mixed triplet singlet. Okay. So, that is what is called as mixed triplet singlet character of new state. So, therefore, so here forbidden 1s to 3p transaction or transition are partly allowed. Okay. So, this is one example. So, where we will see the forbidden transition also, even though if the spin multiplicity is not same. So, due to the spin orbit coupling, there is a chances of transition, electronic transition that could takes place. So, such a type of transitions are called as forbidden transition. Forbidden transition means, so according to the selection rules what we have decided, what we have discussed, so it should reach the required characteristics, even though if the spin multiplicity is different or the quantum number is not changing. So, in spite of that, so the electronic transition could takes place, the electronic transition can takes place. So, such a type of electronic transitions are called as forbidden transitions, and this takes place because of the new state form, where the singlet this 1s2 state and 3p naught state. So, these both combined together. Okay. So, that is what is called as spin orbit coupling. Due to the spin orbit coupling, a new state is formed. So, in that new state, so the transitions are partly allowed. Okay. So, such a type of transitions are called as forbidden transitions. So, I am going to stop it here. So, in my next class we will see what is meant by relaxation of selection rules or breakdown of selection rules. Okay. Thank you, dear students.